All right, let's get started. Acid-base equilibrium. So this is where we talk about buffers. Okay, we talk about titration. We talk about the common ion effect, which gets just a little bit confusing, but we'll make sure that all of you are on the same page on this. Okay. So we've talked about acids, we talked about bases, we talked about Ka, we talked about Kb, we talked about Kw, we talked about pH, pOH, and their relationship. So this is, having understood that, this is the continuation. Okay? So what is a common ion effect? It says it's a shift in equilibrium position that occurs due to addition of an ion already involved in the equilibrium reaction. So you have, let's say, hydrochloric acid, or you have some kind of acid or some kind of base, and whatever the ions that thing gives out, you're putting another compound in with one of the same ions. So think about that's like adding another product, right? You know it's going to shift the equilibrium. Okay. So let's consider something like ammonium chloride. Ammonium chloride dissociates, you get ammonium and you get chloride. Okay? So it says production of extra ammonium ions causes a shift in the position of the ammonia-water equilibrium. And if you had in the same beaker, right, you have ammonia, water, and so you have ammonium and hydroxide. So if you're going to add more ammonium, right, you see how ammonium is found in both of these, both in the ammonia and the ammonium chloride. So if you get extra ammonium production, right, what's going to happen?
It's going to shift.
It's going to shift, and the equilibrium concentration of the hydroxide is going to decrease. So if you have ammonium water already ready to go, and you add ammonium chloride to it, okay, that ammonium is going to take the hydroxide out, right, and probably make a new compound.
Wait, what do you mean if you add the ammonium chloride?
Yeah, so you have ammonium already, and then you add more ammonium chloride. So the common ion is you already have the ion, and you're adding a compound with the same ion in there.
Okay.
So you're going to shift the equilibrium depending on which ion you're adding. Okay? So production of protons by first dissociation inhibits the succeeding dissociations. What do we talk about when we talked about polyprotic acids and their rate of dissociation? The first one is always a lot stronger than the second one. Second one is stronger than the third one. Right? And look at what it says here. It says in polyprotic acid, production of protons by the first dissociation decreases the second dissociation.
The first is stronger than the second?
First is stronger, and also by having those ions, it's not allowing the second dissociation to happen.
Because of...
Okay, and we're going to see why. So let's think about something like this. You have 1 molar hydrofluoric acid, which has a concentration of H plus ions of 2.7 times 10 to the negative 2. Percent dissociation is 2.7%. Hydrofluoric is a fairly weak acid. Now, it's asking you to calculate the hydrogen ion concentration and the percent dissociation of HF, same solution, and then you add 1 molar sodium fluoride. This is your common ion, right? Because you have fluoride here, the HF, and then you're adding a compound that has a sodium and a fluoride into the same beaker.
So you have to know if it's becoming, well, it's going to be a reactant, right?
So what is it going to happen? What is going to happen? That is a question, right? So you know HF dissociates into H plus and F minus. The Ka is 7.10 to the negative 4, weak acid, so it has a small Ka. And so what do you have in solution? You have your HF, right? You have your fluoride ion, and you have your sodium ion. Okay? Yeah. Ice table. So HF initially is 1 molar. Fluoride is 1 molar. So remember how we always put zeros here?
Yeah.
Okay, you see how fluoride now is 1?
Why?
Why?
Because there's another one.
Because what did you start with?
1
1 molar
Of
HF.
Sodium fluoride. Sodium fluoride is very soluble. Remember the solubility rules.
oh. It's
So
not
in
always-
solution, it's sodium and fluoride ion. So now, in the beginning, you already have fluoride ions to begin with. Okay?
Is that always when it's soluble? Like we have to take that into account.
Yeah, well, especially with next chapter when we look at KSPs. Okay. So, H plus in the beginning we're assuming is just 0. Why? Because, you saw the 2.7% dissociation. And then fluoride is 1 molar because of the sodium fluoride. So that changes it just a little bit compared to what you've seen before. Now you have a 1 plus X and a 1 minus X. We're going to make the same assumption we did before. The plus X and minus X really doesn't matter here because look at your Ka, 10 to the negative 4. So it's probably going to be much less than the 5%. So you solve for X, and you get that X is 7.2 times 10 to the negative 4. And then if you wanted to see if you're right, here you go. That's only 0.0072%, so you're still 99% accurate, so you're good. And then once you find your hydrogen ion concentration by solving for X, then you can find your pH. Okay? So, you had 2.7 times 10 to the negative 2 molar hydrogen ion, right? And the percent dissociation. But then once you added the fluoride ions from the dissolved sodium fluoride, then dissociation became even less. Okay? Because the sodium is going to pick up the fluorides too. Oy. Okay. Now, what does it mean for a solution to be buffered? Does anyone remember from, if you've taken AP Bio, you've done buffered solutions.
So only in.
Your blood has to be maintained at a pH of 7.2 to 7.4 all the time. So what maintains it?
Buffers.
Yep.
Wow.
Okay. So these are solutions that resist pH change. When they see that hydrogen ion concentration is increasing, they pick up the hydrogen ion. When they see that there isn't enough hydrogen ion, they dissociate to produce hydrogen ion to make sure that the pH does not change past the point that it's supposed to. So blood is a buffer, and a buffer is really a weak acid and the salt. Okay? And you can buffer at any pH by making the right solution. Not for blood. Blood does its own thing. Okay? Which, it's swelling up.
Oh my god, I'm like losing my mind.
Go ice,
right here.
ice.
have
Go
ice?
get a pack of, we
It's
do
like-
have ice.
It's like making me insane. It's really throbbing.
So, buffers, you have a weak acid and you have a salt that goes with it. Okay? So, a buffered solution really can contain a whole bunch of different combination of things. Okay? And it just, as long as it's a weak acid. So the weak acid here is acetic acid. You worked with that yesterday in the lab. And it has a Ka of 1.8 times 10 to the negative 5. And then you have 0.5 molar sodium acetate in the same solution.
It's Miss H. It's freezing. It's like wow.
Just do it. Full
All right.
How do we know that acetic acid is the weak one?
Once you know your strong acids, everything else is weak. Okay?
Also, the
And
Ka is small.
thank you. Also the Ka,
Is K ever big?
this is a salt, not an acid. It won't have a Ka. Okay? So, how are we going to calculate the pH of something that it has now two things in there? But it does have a common ion, right? Remember the common ion effect. This is going to inhibit the dissociation, right? Acetate is your common ion here. So, here we go. This is what you have. You have your weak acid. Sodium, that's neither an acid nor base, right? Acetate is your conjugate base of the acid, so it's actually a stronger base than the acid is an acid. And then you have water, which is amphoteric, which means it can act as an acid or a base, but it's weak either way.
It's always weak.
So you're dealing with the protons. I don't know where potassium came from. Acetate and acetic acid, right? You know your Ka, you know how it goes. And now you're going to do the ice table. And in this case, again, the acetate, instead of starting with 0, you're starting with 0.5 because that's the sodium acetate that you're starting with. You do the same thing you've done before, right? And you can ignore the minus x and plus x because you're dealing with such a tiny Ka. And you solve for x. Once you solve for x, you find it to be 1.8 times 10 to the negative 5. That gives you a pH of 4.74.
Just near her the last problem we've done, then the Ka has been the same as the concentration of H.
Why? Because both your concentrations were the same, and then because you ignore the minus x and plus x, they cancel that. Okay? Alright, so let's go back for a second. pH is 4.74. Now it says to calculate the change in pH that occurs if you had 0.01 mole of solid sodium hydroxide added to the buffered solution in 15.2, which is the one before. So what do you think would happen if I add sodium hydroxide to a buffered solution that contains acetate and protons?
Does it matter that it's solid?
It'll dissolve.
Okay.
Sodium hydroxide is very soluble.
Yeah.
Stay the same. It's a buffer.
But what would make it stay the same? Okay, so let's do the math here. But before we do the math, here's what's going to happen. You're going to add hydroxide, right? Once you add the hydroxide is going to pick up what in solution?
The H.
The H plus and turn into?
Water.
Yeah. Okay. So, we're going to assume the reaction goes to completion. And we're going to, again, assume that all our stoichiometric coefficients are
How do you
what they
know
are.
whether to add OH or...
Because it said sodium hydroxide. Sodium doesn't really count here. Sodium doesn't do anything. Okay? So once you have your balanced equation, and it said it's 1 liter, so we have to make sure that all our moles are correct, right? Okay. So before the reaction, you have 0.5 moles of acetic acid. After the reaction, you have to subtract how much hydroxide you added to it, because that's how much it's going to take up. And then the other side, obviously, you're adding to it. So you can see the change isn't much, right? And you know that the acetic acid has been converted to acetate once you add hydroxide because it took the hydrogen away from it.
Wouldn't it be 0 for that? Acetic acid?
To start
Or
with,
when it's a product.
here,
Yeah.
the acetate.
Yeah.
The acetate, you start with 0.5 moles, right?
Okay. So it's not...
And then what happens is because you're adding the hydroxide to it, you're actually getting more acetate out of it. Once you add hydroxide, the hydroxide is going to take away the H.
Okay.
So now you have more acetate.
Okay.
As much hydroxide as you added, that's how much acetate, more acetate you're going to have. Okay. So now your new ice table looks like this. Okay.
I just realized that Eli can't see that little.
That's okay. Well, he still has the power.
Sorry,
So
Eli.
now the pH is 4.76.
What was it?
What was it before? 4.74. So it's not much of a change, right? Because it is a buffered solution. And it's going to take it up. Okay? So the change is 0.02. And comparing the value of the 0.01 moles of solid sodium hydroxide, if you think about it, the pH of sodium hydroxide with 0.01 molar is like pH of 2. But you add it to 4.74 and it's not going to, pH of 12. But it's not going to increase it much, right? Okay, because if you had just pure sodium hydroxide, you have a pH of 12. But that's not the case when you have a buffered solution. Okay? All right, we'll take a break, come back at 8. So, back to buffered solutions. So, we're going to solve these things, and the solution is going to be a little different, and then we'll talk about the titration afterwards and the importance of all that good stuff. So, you're going to have a buffered solution with some pH, right? And then once you add the hydroxide or hydrogen ion, then it's going to be modified. So you'll do regular calculations, and then you'll do the equilibrium concentration calculations to figure out what's going on and how the pH changes. And you're going to see that the pH shouldn't be changing much, right? Because if it's a buffered solution, it should be able to take up an H plus and an OH minus, or release it and so on. So consider a buffered solution that has a large quantity of weak acid and a whole bunch of its conjugate base. And you add hydroxide ion to this buffered solution. When you add the hydroxide ion, what does the hydroxide ion do?
Hey.
It takes the what?
The hydrogen ion.
The hydrogen ion from HA, leaving you with
Water.
A minus and water. Right?
Wait, so water is the conjugate, or it's not, because it's amphoteric, but like, wouldn't it?
Yeah. So here, if you're considering OH your base and HA is your acid, right? So A minus is your conjugate base, it would be your conjugate acid. Because it has the ability to give up an H. Very good. So, you add your hydroxide, you're going to have a final pH. You start with some original pH, and the hydroxide will take away the H pluses and will be replaced by A minus, right? So that's what makes it not change its pH so much, because instead of having a whole bunch of hydroxide in solution, now you have a whole bunch of A minus in solution. So, you know how to calculate Ka, and if you were to solve for your hydrogen ion solution, you're going to see that it's a ratio of HA and the A minus. So HA can be any acid, and A minus is the conjugate base of that. So if you have a lot of, if the amounts of HA and A minus originally are large amounts compared to hydroxide, then the change is going to be really small. So when you have a small amount of hydroxide added to large amounts of HA and A minus, the concentration changes are going to be small, and so the pH will remain constant. And that's kind of the whole point to a buffer, right? To have pH remain constant.
So you want to add a small concentration.
Basically, because whatever you're going to add, you're not going to add in this large amount that it can't buffer, right? And that's kind of how it happens, because if it is, then chances are it's going to take a little bit for it to go back to normal. So, again, you add hydroxide, and your ratio is going to be very close to the original because you have a lot more HA and A minus compared to the hydroxide that is added. Now, what if you add protons, now hydroxide, to the solution? Then what are you going to have?
You're going to have the conjugate base.
The A minus is going to be now taking out a solution, right? But as long as that ratio is still larger than the H plus you add, would you expect much of a change?
No.
Nope. That's the whole point. Now, the Henderson-Hasselbalch equation, basically using this whole idea of the ratio and the buffered solution and all that, and getting the pHs, and I think this is on your sheet. pH is pKa, so the negative log of a K, minus log of HA over A minus. Okay, and those are concentrations. Okay, so what it really comes out to is, in order to find pH of a buffered solution where you have both an acid and a base in solution, because you do have the acid and the conjugate base, right? You're really getting the pKa, which is the negative log of your Ka, and then you just need your concentration of your base and your acid. Once you have that, you can find pH, and we'll see how that works. All right, so for a system that's a buffering system, if you have the same ratio of A minus to HA, regardless of what the concentration is, the ratio is the same, then you expect your pH to be the same.
The pH depends on the ratio.
Okay?
That makes
If you're dealing with the same thing, right? Because they all have the same Ka. And according to Henderson-Hasselbalch, pH is pKa plus the log of the A minus over HA, right? Base over acid.
You need to know who he is.
So, based on the table, if you have this, the negative, the acetate and the acetic acid buffering system, and you have your pKa at 4.74 because you know your Ka for acetic acid, and you find the concentrations, you're given the ratio, and you see that the pH becomes 4.52. So the assumption is the equilibrium concentrations are equal to initial concentrations.
How
Okay.
is it plus in that case? Because you do minus the log.
That's the equation is pKa plus the log.
Oh, I thought it was minus the log.
It's plus log. That's why it ends up being negative. Now, let's look at a buffered solution. You have 0.25 molar NH3 with a Kb of 1.8 times 10 to the negative 5. And you have 0.40 molar ammonium chloride. How would you find the pH of a solution like this?
Find the pH of the ammonia, right? Because that's your, the weak acid is your, no, there's no weak acid.
No, it's like the common ion, right? Because there are two of them.
There are, yeah. You have a base, and you're adding
So because
you're adding a very soluble salt, right, which is ammonium chloride, to your base. How would you find the pH of that? First of all, what are you dealing with? What do you have in solution? You have your ammonium and you have your hydroxide, right? Because it's a base. You got to get your hydroxide from somewhere. Okay. And you know your Kb is 1.8 times 10 to the negative 5, and you have ammonium hydroxide over ammonia. So, the ice table, since you start with 0.25 ammonium, 0.25 ammonia, and you start with 0.4 ammonium, because it comes from the ammonium chloride, right? You do your regular ice table, and you plug in, and you solve for X. X becomes 1.1 times 10 to the negative 5. By approximation rule, you're good. But your X here is hydroxide, not hydrogen, right? You don't have hydrogen here. So then once you find your pOH, can you find pH? How? Like this. Okay? So initial and equilibrium concentrations of the buffering materials are pretty much the same. Now, your alternative solution to this, you know your Kw, because that's a constant. You were given Kb. Now you can solve for Ka. Once you solve for Ka, then you can do Henderson-Hasselbalch. Where all you're doing, Hasselbalch. So 9.25, because that's the Ka, right? And it's a negative log of Ka. And then the log of concentration of your base and your acid. Your base is the 0.25, right? And the acid is the conjugate acid of that, which is really your salt, 0.4. And then you plug in. You plug into your calculator. Okay? So, buffers are dependent on what they can absorb and what they can release, right? If you have a buffered solution and you add a really strong, a whole bucket of strong acid, no matter how good the buffer is, it's going to shift a lot more than you wanted it to. So amount of protons or hydroxide ions that a buffer can absorb without a significant change in pH, the larger the capacity, more concentration. So it all depends on what kind of buffered solution you're talking about, but all of them can take in small amounts of hydroxide or hydrogen without changing the pH much. Okay, that's kind of the whole point to a buffered solution. All right, so we're going to stop there, and I'm going to give you some problems.